Voyager 1, launched September 5, 1977, is the most distant human-made object in existence. As of January 2026, it's traveling at 38,000 miles per hour, 17 kilometers per second, through interstellar space, over 15 billion miles from Earth. That's 170 astronomical units. 170 times farther from the Sun than Earth is. But here's the paradox: despite being built with 1970s technology, computers with less processing power than a modern car key fob, transmitters that draw less power than a refrigerator light bulb, we still receive data from Voyager every single day. Clear, scientific measurements from a region of space no human-made object has ever reached. How is it possible to communicate across 15 billion miles with a 23-watt transmitter? And how much longer will we be able to hear Voyager's voice before the darkness swallows it forever? The answer might surprise you. Because in 2026, NASA is fighting a war against physics itself to keep humanity's furthest ambassador alive. When NASA began planning Voyager in the early 1970s, engineers faced a problem that seemed almost comical in its audacity. They were designing a spacecraft to visit Jupiter and Saturn, a 4-year mission. But there was a catch. A once-in-176-year alignment of the outer planets was approaching. If they launched in 1977, they could use gravity assists to visit all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune. A grand tour that would normally require 4 separate missions and decades of time. But here's the counterintuitive detail: Voyager 2 launched first, on August 20, 1977. Voyager 1 didn't launch until September 5, 16 days later. Yet Voyager 1 is called 1 because it was on a faster trajectory, arriving at Jupiter 4 months ahead of its twin. The naming wasn't about launch order. It was about finish order. The original mission plan was simple: fly by Jupiter and Saturn, take pictures, gather data, then drift into the cosmic void and die. 4 years maximum. After that, the spacecraft would run out of hydrazine fuel for course corrections, or the instruments would fail from radiation damage, or the power supply would fade to nothing. Nobody expected them to still be operating in 2026. During the primary mission from 1977 to 1989, the twin spacecraft revolutionized our understanding of the outer solar system. Voyager 1 discovered active volcanoes on Jupiter's moon Io, the first active volcanoes found beyond Earth, with eruption plumes reaching 300 kilometers high. It found that Saturn's rings weren't smooth bands but thousands of individual ringlets, braided and twisted by shepherd moons. The iconic pale blue photograph of Earth, taken on February 14, 1990, from 3.7 billion miles away, showed our entire planet as a single pixel suspended in a beam of scattered sunlight. Voyager 2 became the only spacecraft to ever visit Uranus and Neptune. At Uranus in 1986, it found a planet tipped on its side, rotating at a 98-degree angle, with a magnetic field tilted 59 degrees from its spin axis, completely unlike any other planet. At Neptune in 1989, it discovered the Great Dark Spot, winds reaching 1,500 miles per hour, the fastest in the solar system, and geysers of liquid nitrogen erupting from the surface of Neptune's moon Triton. After Neptune, the mission should have ended. The cameras were shut off permanently in 1990 to save power. The last photo ever taken, the family portrait of the solar system, showed 6 planets in a single mosaic. Then the imaging system went dark forever. But the Voyagers kept flying. And in doing so, they achieved something far more profound than photographing planets. By 2012, Voyager 1 had traveled so far that it crossed the heliopause, the boundary where the solar wind stops and interstellar space begins. It had left the Sun's domain entirely. Voyager 2 followed in 2018, crossing at a different location and providing the first multi-point measurements of the heliosphere's edge. Here's what makes this remarkable: the two spacecraft took different paths and crossed the heliopause at different distances. Voyager 1 crossed at 122 astronomical units. Voyager 2 crossed at 119 Australian dollars, closer to the Sun. This revealed something profound: the heliosphere isn't spherical. It's asymmetric, squeezed by the pressure of the interstellar medium flowing past our solar system like water flowing around a rock in a stream. Right now, as of January 2026, Voyager 1 is in a region called the interstellar medium. This may not seem like much, it's still space, after all, still a vacuum. But imagine you've lived your entire life in a house where every room has air conditioning running constantly. You can hear the hum, feel the air pressure, sense the environment around you. Then one day, you walk outside for the first time. The hum stops. The pressure changes. You're in an entirely different environment that operates by different rules. That's what Voyager 1 experienced when it crossed the heliopause. The solar wind, a constant stream of charged particles from the Sun, dropped to zero. The galactic cosmic rays from interstellar space increased dramatically. The magnetic field shifted from the Sun's organized field to the chaotic, turbulent field of the local interstellar cloud. Voyager is now measuring a region of space that has never been sampled by human instruments. Every data point is new. Every measurement is a first. The plasma density, the magnetic field strength, the direction and intensity of galactic cosmic rays, all of it is expanding humanity's knowledge of the galaxy we live in. Before we go further, let's clarify two terms that people often confuse: the heliosphere and the solar system. The heliosphere is the bubble of charged particles and magnetic fields created by the Sun's solar wind. Think of it like the wake behind a boat, the region where the boat's motion is still affecting the water. The heliopause, where Voyager 1 and 2 crossed, is the edge of that wake. Beyond it, you're in the open ocean, the interstellar medium. The solar system, on the other hand, is defined by the Sun's gravity. It extends far beyond the heliosphere, all the way out to the Oort cloud, a spherical shell of icy objects that reaches roughly halfway to the nearest star, about 1 light-year away. Voyager 1 won't reach the edge of the solar system for another 300 years. It won't reach the Oort cloud for 300 years. It won't escape the Sun's gravitational influence for 30,000 years. So when did Voyager cross from one to the other? The exact moment was August 25, 2012, for Voyager 1, and November 5, 2018, for Voyager 2. Scientists knew they'd crossed because the plasma wave instrument detected a sharp change in electron density. The spacecraft had been in a region where electrons were sparse, about 0.08 electrons per cubic centimeter. Suddenly, the density jumped to 0.13 electrons per cubic centimeter. That doesn't sound like much. But here's the significance: it proved Voyager was no longer surrounded by the solar wind's charged particles. It was measuring the background density of interstellar space, a medium that fills the space between stars across the entire galaxy. To put this in context, here's a multi-stage timeline. From 1977 to 1979, Voyager traveled to Jupiter, which took 2 years. From 1979 to 1981, it traveled from Jupiter to Saturn, another 2 years. From 1981 to 1989, Voyager 2 continued from Saturn to Neptune, which took 8 years. From 1989 to 2012, it took 23 years to travel from Neptune to the heliopause. And from 2012 to the present has been 14 years and counting in interstellar space. Voyager has been in interstellar space longer than it spent visiting all 4 outer planets combined. Here's the core mystery at the heart of the Voyager mission: how can a spacecraft 15 billion miles away, built with 1970s technology, still talk to Earth? Let's start with the transmitter. Voyager's main radio transmitter outputs 23 watts of power. For comparison, a typical refrigerator light bulb uses 40 watts. A standard Wi-Fi router transmits at 1 watt. Voyager's signal, the one carrying scientific data across billions of miles, is only 23 times more powerful than your home internet. Now consider the distance. As of January 2026, Voyager 1 is 15.8 billion miles from Earth. That's 170 astronomical units. Let's use a perspective ladder to understand that scale. The Moon is 1.3 light-seconds away. Voyager's signal takes 23.6 hours to reach Earth, over 65,000 times farther. Mars at its closest is 3 light-minutes away. Voyager is 473 times farther than that. Pluto at its average distance is 5.5 light-hours away. Voyager is more than 4 times farther than Pluto. When Voyager transmits a signal, that signal spreads out in all directions like ripples on a pond. By the time it reaches Earth, the 23-watt transmission has spread across an area trillions of square miles wide. The intensity follows the inverse square law, double the distance, and the signal becomes 4 times weaker. At Voyager's current distance, the signal arriving at Earth is just 0.1 billion billionths of a watt. That's 10 to the power of -19 watts. To put that in perspective, if you collected all the radio energy Voyager has transmitted to Earth over its entire 47-year mission, it wouldn't be enough to power a single snowflake falling to the ground. So how do we hear it? The receiver has to be massive. NASA's Deep Space Network operates 3 facilities spaced equally around Earth, in California, Spain, and Australia, to ensure 24/7 coverage as the planet rotates. Each facility has multiple antennas, but only one antenna can communicate with Voyager, the 70-meter dishes. These dishes are among the largest radio antennas on Earth. The main dish in Canberra, Australia, Deep Space Station 43, is 70 meters across. That's 230 feet, roughly the size of a 20-story building laid on its side. The collecting area is over 4,000 square meters. It takes that much surface area to capture enough of Voyager's signal to decode the data. Even then, the data rate is agonizingly slow. At Jupiter, Voyager could transmit at 115,200 bits per second, faster than a 1990s dial-up modem. By Saturn, that dropped to 44,800 bps. Today, at 170 Australian dollars, Voyager 1 transmits at just 160 bits per second. That's barely enough to send a single tweet in 10 seconds. A single image would take days to transmit. Which is why the cameras were shut off permanently in 1990. There's no point taking pictures when you can't send them home. But here's the ticking clock: Voyager can't keep transmitting forever because it's running out of power. When most spacecraft run out of fuel, they die. But Voyager doesn't use solar panels or rechargeable batteries. It uses 3 radioisotope thermoelectric generators, RTGs, that convert the heat from decaying plutonium-238 into electricity. At launch in 1977, each RTG produced 157 watts. Collectively, the 3 RTGs generated 470 watts, enough to power the entire spacecraft, all its instruments, transmitters, heaters, and computers. But plutonium-238 decays with a half-life of 87.7 years. Every year, the RTGs produce slightly less power. It's not a switch that flips. It's a slow, inexorable decline. By 2011, Voyager 1's power output had dropped to 268 watts, about 57% of launch capacity. As of 2026, it's down to approximately 220 watts. The engineering team has been fighting this decline for decades. They've turned off heaters, one by one, allowing non-critical systems to freeze. They've shut down redundant systems. They've disabled the gyroscopes and switched to celestial navigation using star trackers. They've even turned off the main radio receiver and rely on a backup system that uses less power. But eventually, they run out of things to turn off. The most emotional moment came in 1990, when Voyager 1's imaging system was shut off permanently after taking the pale blue photo. The camera that had captured the volcanoes of Io, the rings of Saturn, the clouds of Jupiter, silenced forever to save 7 watts of power. Today, Voyager 1 operates with just 3 scientific instruments still active: the magnetometer, measuring the interstellar magnetic field, the plasma wave instrument, detecting electron density, and the cosmic ray subsystem, counting high-energy particles from outside the solar system. That's it. 3 instruments. The rest have been sacrificed to extend the mission. And the power continues to decline. Voyager 1 loses approximately 4 watts per year. At the current rate, engineers project the mission will run out of power to operate even a single instrument sometime between 2032 and 2036. After that, Voyager will still be flying, it will continue traveling through interstellar space for millions of years, but we will no longer be able to hear it. Voyager's journey has been punctuated by crises that should have killed the mission. Each time, engineers found a way to save it. In 2017, Voyager 1's attitude control thrusters, the tiny jets that keep the antenna pointed at Earth, began to fail. These thrusters fire in pulses lasting just milliseconds to nudge the spacecraft's orientation. After 37 years of constant use, the fuel inside the thrusters had left residue on the internal components, clogging the valves. If the thrusters failed completely, Voyager would lose its ability to point its antenna. The signal would drift. We'd lose contact. Game over. The solution was audacious: switch to the backup trajectory correction maneuver thrusters. These thrusters hadn't been used since November 1980, 37 years earlier, during Voyager's Saturn flyby. Engineers sent the command, knowing there was a real chance the thrusters wouldn't fire after decades of dormancy. On November 28, 2017, the TCM thrusters ignited perfectly. Voyager 1 was saved. The spacecraft could point its antenna for another 2 to 3 years before even those thrusters degraded. In 2022, Voyager 1's attitude articulation and control system began sending garbled telemetry data. The spacecraft seemed to be working fine, it was still oriented correctly, still transmitting science data, but the AACS was reporting impossible readings about the spacecraft's orientation. Engineers spent months diagnosing the problem. Finally, they discovered the issue: the AACS had started routing telemetry through a dead computer that had been offline for years. For unknown reasons, possibly a cosmic ray bit flip, the system had begun sending data to the wrong memory address. The fix required a manual workaround: reprogram the AACS to route data through the correct computer. In May 2022, the patch was uploaded, and Voyager's telemetry returned to normal. Between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the only antenna capable of sending commands to Voyager, is offline for upgrades. This created a critical deadline. If Voyager developed a problem during this blackout period, engineers would have no way to send commands to fix it. The proactive solution: before the blackout began, NASA uploaded contingency software patches to both Voyagers. The spacecraft now have automated routines to handle common problems without ground intervention. If a thruster clogs, the spacecraft will automatically switch to backups. If a voltage fluctuates, it will stabilize itself. This gives Voyager the best chance of surviving the upgrade period. The antenna is expected back online in February 2026, with enhanced sensitivity that should extend the mission by several more years. The challenges are ongoing. Every day could be Voyager's last. But every day, it continues to transmit. In 2026, NASA announced the next instrument shutdown. Voyager 2's cosmic ray subsystem will be turned off later this year to conserve power. After that, 4 instruments will remain active. Then 3. Then 2. Then 1. The final shutdown is projected for 2032 to 2036. At that point, the RTGs won't produce enough power to run even a single instrument and a transmitter simultaneously. Engineers will have to choose, science, data, or communications. When that day comes, they'll choose communications. Voyager will stop doing science and use its last watts to simply say, "I'm still here." Engineering telemetry only. Temperature readings. Voltage levels. Confirmation that the spacecraft still exists, still functions, even if it can no longer tell us about the universe around it. Then, a few years later, perhaps in 2036, perhaps as late as 2040 if the RTGs perform better than expected, even that will end. The transmitter will fall silent. Voyager's voice will fade into the cosmic background noise. And humanity's link to its furthest explorer will be severed forever. After that, Voyager will fly on in silence. In 40,000 years, it will pass within 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis. In 296,000 years, it will pass Sirius, the brightest star in Earth's night sky. In 2 million years, assuming it doesn't collide with anything, it will have traveled 4.3 light-years, roughly the distance to Proxima Centauri, the nearest star to our Sun. But by then, no one on Earth will remember the spacecraft exists. The golden record it carries, a message from humanity to any civilization that might find it, will be the only evidence that we were here. Voyager launched in 1977 with a planned mission duration of 4 years. It has now operated for 47 years and counting, nearly 12 times longer than designed. The spacecraft was built with 69 kilobytes of computer memory. Your smartphone has 1,000,000 times more. Its main computer operates at 250,000 instructions per second. A modern iPhone executes 5 trillion instructions per second, 20 million times faster. The camera system that photographed Jupiter's Great Red Spot had a resolution of 800 by 800 pixels. The data storage tape recorder could hold 536 megabits of data, about 67 megabytes, less than a single MP3 song. And yet, this ancient technology, this relic from the age of disco and analog television, has achieved something no modern spacecraft ever has. It left the solar system's protective bubble and ventured into the space between the stars. In 2026, Voyager 1 will reach 1 light day from Earth, the distance light travels in 24 hours. That's 170 Australian dollars and 20 cents, or 15.8 billion miles. It will be traveling at 38,000 miles per hour relative to the Sun, never slowing, never stopping. And it will continue to travel through interstellar space, through the local interstellar cloud, through regions we have no names for, carrying its golden record as a message in a bottle cast into the cosmic ocean. Long after we've lost contact. Long after the mission ends. Long after everyone who built it has died. Voyager will keep flying. Forever.